So today we're going to do some practice on intermolecular forces. And if you remember, intermolecular forces are experienced from one molecule to a neighboring molecule, or from one atom to a neighboring atom. They are not forces felt within the molecule itself. So the question number 3 on your homework has 2 parts to it. So the first one asks, what types of intermolecular forces are felt by these following compounds? So the rule of thumb is dispersion forces are felt by everything. So we could say dispersion forces are felt by all of them, right? That's the rule of thumb. Dispersion forces are felt by everything. But now let's move on up and see what kind of forces we have going on. So I did make that one chart that, if it helps, hopefully, it's uploaded under course documents, but I talk about this kind of stuff. So carbon and hydrogen, when they're bound together, carbon and hydrogen are basically assumed to be nonpolar. So if you have a compound with only carbon and hydrogen, it will always be nonpolar, right? So it doesn't have any of that polarity. It does not have dipole moment. It doesn't have any it doesn't have hydrogen bonding, nothing like that. So if it's only carbons and hydrogens, it will be dispersion only. So this one is dispersion only, so that's it. We're going to wrap him up. We know that for a fact. This CH4 also fits that category. Only dispersion forces are felt, right? The other ones have something different going on. So what we're going to look at is those compounds. So let me double check the way that it's worded on the homework. Dispersion and dipole. Okay. So remember that H bonding, hydrogen bonding, is a type of dipole-dipole. So we have one little nugget of wisdom here. Remember that H bonding is type of dipole-dipole, right? So if you have hydrogen bonding, you must have dipole-dipole bonding as well, right? So let's take a look at this formula. As it's written, it's telling us that we have carbons and hydrogens bound, and then we have an oxygen bound to a hydrogen. So remember the rule of NOF. You have to have a hydrogen bound to either nitrogen, oxygen, or fluorine inside the molecule itself. So in this case, we have an oxygen bound to a hydrogen. So this will display hydrogen bonding. So it also displays dipole-dipole. Right? So we can wrap this up. So that's the answer for this one. And then this compound, if you remember, this was actually on the exam. It's H bound to C, triple bound to an N. I don't see, and I probably would draw this for you on an exam if I was asking you to classify it. But the first thing I notice is that this does not pass the rule of NOF. There is no there's no hydrogen bound directly to a nitrogen, oxygen, or fluorine. So this is no H bonding here, right? But we do have a nitrogen, which is very electronegative, and a hydrogen, which is very positive. So we have partial negativity and partial positivity. And that, my friends, is a dipole, right? Dipole is an overall polarity throughout the compound. So we have dispersion here, and we have dipole-dipole. That's all we have for this one. The last one is NH3, which is nitrogens bound to a bunch of hydrogens. So if you guys remember, this was also on the exam. Nitrogen bound to a bunch of hydrogens. So not only is nitrogen bound to the hydrogens, it's also polar, right? Because these are slightly positive and this is slightly negative. So this has dipole-dipole, and it's also got hydrogen bondings because H is bound to NOF, N-O or F. So this has dispersion, it has dipole-dipole, and it has H bonding. So I know it's a little rough to read here because I'm trying to organize it, but you can, as if you followed along with me, you can figure out, right? So let's go down here, and these ones down here, this is a little trickier. It's asking us to order them in order of boiling points from highest to lowest. So when you're doing this, when you're doing boiling points or melting points, so you're doing boiling point or melting point, right? What you need to do is you need to find strongest force and use that to list them. So the strongest force involved in HI, the strongest force involved in H2, and the strongest force involved in CH3OH, right? So the strongest force is here. So if I were to look at HI, that would be an H bound to an I, right? And I is on the right-hand side, so it's very electronegative. This is very positive, so we have a slightly positive, slightly negative. So this is a dipole, is the strongest. So dipole, dipole is the strongest here, right? For HI. H2 is just two H's bound to each other. So is there any difference in electronegativity? No. So it does not have a dipole-dipole moment. So what's the only intermolecular force it can have? Dispersion. Right? And then lastly, we have a CH3, and it's written this way, and then it's bound to an O and an H. So the O and the H are bound together. This has the rule of NOF, right? It's bound to an NO or F. A hydrogen is bound to an NO or F. So this one has H bonding. So we're going to order them in order of boiling points. The highest boiling point. So how can we wrap our head around this? The stronger the intermolecular force, the higher the boiling point. So we can know that as a relationship. So the stronger the intermolecular force, I abbreviate that IMF, the stronger the intermolecular force, the higher the boiling point or melting point. Why? Well, that's because if this has H bonding, you could picture a CH3 methanol and another neighboring methanol. If they have a strong intermolecular force, you picture that like, remember the dotted line here, and we have a neighboring CH3OH, right? This is going to be strong because this hydrogen bonding is relatively strong when we compare it to, let's say, an H2 and an H2. What kind of attraction do these guys have? Remember the dipole-dipole when the cloud just happens to move along. So this is very weak. This is a very weak attraction. I'm going to even draw like this is weak. I'm going to put a sad face. Not very good. So would we have to give more energy to break this up and turn it from a liquid to a vapor? Yes, this requires more energy to break apart and to move these apart from one another. Whereas these two aren't very attracted to each other, so they're very willing to move apart, right? So the rule of thumb is the stronger the intermolecular force, the higher the boiling point or melting point. So we can list them here. This is the strongest intermolecular force, so this would have the highest. This is the weakest, so this would have the lowest. And HI is in the middle, so this would be the middle. So I hope this helps. I know I wrote a whole lot on this, but if you follow along, please just let me know if you have any questions. Good luck!